The p-series looks like this, where the exponent p is a value bigger than 0. So these are all p-series. P is 1, p is 1/2, p is 3, p is 3/5. These are not p-series. P, the exponent of n in the denominator, has to be positive, not a p-series. If we wrote n in the denominator, it'd be n to the negative second, so not a p-series. This one is a p-series. At least it's 5 times a p-series. Last thing to mention on this page is this p-series with a p-value of 1. That gives us the series 1 plus 1/2 plus 1/3 plus 1/4 and onward, and that is the famous harmonic series, and it diverges. In class, we use the integral test to show that this series diverges, and the integral test showed that this series converged. So when p was 1/2, the p-series converged. When p was 1, the series diverged. Or in other words, this infinite sum grows unbounded, while this one converges to some fixed value, let's call it L. Was there some general way of telling for which p-values does a p-series converge? There is, and in this next slide, we're going to prove it. All right, this is the general form of the p-series. Does it converge or diverge? We will use the integral test to determine when it diverges and when it converges. Recall for the p-series, it's only a p-series if p is a value bigger than 1. And it can be a real value. It doesn't have to be an integer value, whole number value. All right, so the integral test, here we go. Let's name it. Let's define our continuous function that generates all the terms of this series for those values of x. And let's check the 2 necessary requirements that this function is decreasing and positive. We know it's decreasing because as x gets bigger, the denominator is getting bigger, which means our fraction is getting smaller and smaller. Remember, p isn't a variable. P is a fixed constant. We could also find that the first derivative, which is this expression, and if p is a constant, bigger than 0, then our numerator is negative. And if x values are bigger than or equal to 1, raised to a positive exponent, that's positive, and negative divided by positive is negative. It's always less than 0, which means the slope is always negative, which means it's always decreasing. All right, next thing to check. Show that the function is always positive for x values bigger than or equal to 1. Well, that's pretty obvious since x itself is positive and p is positive. Clearly, this will always be positive. We can just check that. All right, time for the integral test. What is the definite integral from 1 to infinity of this function 1 over x to the p power dx? Maybe rewrite it first, and then just do the power rule. Add 1 to that negative p. But remember, if you went backwards and took the derivative, it would be negative p plus 1 multiplied by x to this power minus 1, which is just negative p. So we need this denominator so that that negative p plus 1 factor in front of the x, when you take the derivative, cancels out with this negative p plus 1. All right, now let's use the fundamental theorem of calculus part 2, or part 1 actually, and evaluate this. Substitute b in for x, and then minus substitute 1 in for x. Now as b approaches infinity, there's no b's here. P is a constant, so this is just 1 over whatever that negative p plus 1 is. So it's just some constant value. So what about this first term? Now b is approaching infinity, so we have to do with that. Well, if the numerator is approaching infinity, then this entire expression is unbounded and diverges toward infinity. But if the denominator is approaching infinity, then a constant over infinity, that's basically 0. Well, you might say, wait a second, if b is approaching infinity, then how will the denominator ever approach infinity? Well, it would if the exponent on b, which is approaching infinity, was negative. Because if this is a negative exponent overall, then b could be written in the denominator with a positive exponent. And as b approached infinity, our denominator would be approaching infinity, and this whole thing would go to 0. But if the exponent is positive, then it stays up top. And this entire expression approaches infinity, so it's unbounded. So we have to consider the case when the exponent is positive versus when the exponent is negative. Well, the exponent negative p plus 1 is positive when negative p is bigger than negative 1, which is when p is smaller than 1. And when that thing is positive, the b stays up top. As the b approaches infinity, this expression goes toward infinity. Infinity over a constant is infinity. And so in that case, when p is less than 1, we have a diverging series. But when this exponent, negative p plus 1, is negative, then this b base is going to go to the denominator with a positive exponent. So when is it negative? Well, it's negative when negative p is less than negative 1, or when p is bigger than 1. And when that's the case, our exponent is negative, this whole thing, then b is going to go to the bottom. And when it's in the bottom and approaching infinity, we have a fraction where the denominator is approaching infinity. And so this is going to go to 0. So our entire definite integral goes to 0 minus c, or just negative c, which means it's converging. So our series will converge. When the exponent was bigger than 0, positive, as b approached infinity, this is approaching infinity over negative p plus 1. That gives us a divergent term. So the definite integral diverges. Remember, we're doing the integral test here. So the definite integral diverges in that case, so our series will diverge. On the other hand, when the exponent is less than 0 or negative, so if b is to a negative exponent, it will be b to the positive exponent on the bottom. And as b is approaching infinity, we have 1 over something approaching infinity or negative infinity, which is basically 0, which means that our definite integral in that case is converging. And that would mean our entire series is converging. So for p series, when the p-value is less than 1, the series diverges. And when the p-value is bigger than 1, it converges. And when the p-value is equal to 1, we know that's a harmonic series, it diverges. So in summary, this is the definition of a p series. P is a constant bigger than 0. And it diverges when p is bigger than 0 and less than or equal to 1. It converges for any p-value greater than 1. So for a couple of examples, to wrap this up, p is 1, diverges. P is 3, converges. P is 1/2, it diverges. P is 3/5, it diverges. P is 5/3, which is bigger than 1, so it converges. In this case, again, p is 1/3. Even though the 5 isn't part of this standard form, we can just think of the 5 in front. And so this p series, 1 over n to the 1/3, has a p-value of 1/3, which is small enough to cause the series to diverge. Divergent. All right, now it's safe to try all the practice problems assigned. And enjoy your 5-day weekend. Yes, 5 days, Thursday, Friday, Saturday, Sunday, and Monday.